Hey, AP Chem. We are going to be talking today about how you get a KSP value from data that you are given in either a lab experiment or in a problem that you're given on the AP exam. So in 9.1, we talked about how if I give you the KSP value, you can find the X value, which is our solubility, and that can let you know the concentration of each of the ions in solution. Well, if you go the other direction and you're given that information, you can find the KSP value. And so in our class, we're going to be doing that using a lab activity, but we're also going to take a look at an FRQ to kind of talk about that. So way back when we talked about equilibrium, we talked about how if you have the values of all of the things in your equilibrium expression, you can just plug them in and get your K value. And that is true in a solubility problem as well. So if you are able to solve or are given enough information to know the concentration of one of the things that's in solution, okay? And we're assuming at this point where, I should back up, we're assuming that you have just that thing dissolved in that solution. So if you know one of the ion concentrations that are dissolved in solution, you should be able to find the rest of them. So if we look at this example, this is silver phosphate, Ag3PO4. When it dissolves into water, it breaks up into 3 silver plus ions and then a phosphate ion, right? So what happens is if I know that at equilibrium, my concentration of silver is a certain concentration, I can figure out what my concentration of phosphate must be. And then if I plug them into my KSP expression, I'm going to be able to get the KSP. So if I know my silver concentration and I know my phosphate concentration, I can figure out my KSP value. The other way I could do it is if I know my phosphate concentration at equilibrium, it also clues me in as to what my silver concentration is, and then I can also find my KSP. So there's a couple things at play here. There is figuring out what that concentration is, and honestly, reviewing molarity isn't going to hurt you because it's something that a lot of students struggle with. And then additionally, paying attention to stoichiometric ratios, because we know at equilibrium, we should expect to see 3 times the concentration of silver compared to the phosphate. And if we keep those things in mind, it becomes really easy to figure those things out. Now, I'm going to show you guys an FRQ question here from one of the AP exams. And this is one part of a very large FRQ. So on your AP exam, there are right now 10-point FRQs and 4-point FRQs. This is part of a 10-point FRQ. And so there's kind of a lot going on here, but we will go over all the different pieces together. So I'm going to get us into our trusty doc cam, and then we will work this problem out here. Okay. So this is actually, I believe it's the 2015 exam. And if we take a look at the FRQ to start off with, it tells us to answer the following questions about the solubility of some fluoride salts of alkaline earth metals. So alkaline earth metals are our +2 oxidation number metals, just in case you forgot. So for A here, it says a student prepares 100 milliliters of a saturated solution of MgF by adding 0.5 grams of solid MgF to 100 milliliters of distilled water at 25 degrees Celsius and stirring until no more dissolves. And then it says, assume that the volume of the undissolved MgF is negligibly small. Sorry, struggling with the words there. So when they say that, it's just saying that you can assume that the 100 milliliters is all of the solution. It's not that there's this huge pile of stuff stuck at the bottom of the beaker that's taking up more than 100 milliliters for our total volume of solution. Okay, and it says the saturated solution is analyzed and it is determined that the F- concentration is 2.4 times 10 to the -3rd. So when I read through this, if it tells me no more solid dissolves, and it tells me the word saturated solution here, that lets me know that I have in my little container here, I'm going to quick change my resolution. Oh, good. I'm going to have in my container here a teeny tiny bit of solid in here, but then up in this top part of the beaker in solution, I'm going to have Mg+2 in whatever saturation point it is, and then twice as many F minuses. So if you think about how that's going to dissolve, that means that I got a little solid here, but that I have some of this F minus dissolved and some of the Mg. And it's telling me that that concentration is F minus right here, and it's 2.4 times 10 to the negative third molar. So if I take a look and try number 1, it says to write the chemical equation for the dissolving of solid MgF in water. And the reason why they put this on here, it's the first point, it's usually the easiest point. It's to see if you can catch this here. So we know that fluorine is part of our diatomic gang, where we have things that come in diatomic pairs. However, that's only in its elemental form. When it's fluorine, when it's the fluoride ion, when it breaks apart, it doesn't need to be partnered with another fluorine. So my equation in this case is going to be MgF2 solid in equilibrium with its Mg plus 2 ion, and then 2 F minus ions. Be very, very careful when you write these equations. I see a lot of kids writing F2 minus like that. That is not correct. It's 2 F minuses, because when it gets that extra charge, that negative coming from wherever it gets it from, it doesn't need to be partnered up because it's got a full octet. So going through this would be your first answer. 1 point should be hopefully easy peasy, gimme point. All right, then it says calculate the number of moles of MgF2 that dissolved. Now, this is one of those things where there's enough information in the problem, and I didn't go all the way down through the rest of the FRQ, but when I was initially looking at this, I was like, oh, I'm going to use this number, 0.5 grams of solid MgF dissolved in here. But the trick is that it says no more solid dissolved. So we don't know how much solid has dissolved because this is an equilibrium situation. And if you're looking for further hints at its equilibrium, it talks about the KSP down here. So what we have to go off of in this case is right here, the concentration of the F minus ion. Because I did the math and the concentration of this what all dissolved is much higher. So this is the concentration of the F minus. So if I want to figure out the moles of MgF2 that dissolved, the first thing I've got to figure out is how many moles of the fluoride ion I have. And so that's where this volume is going to be important. So if I have a 0.1 liter solution and I know that my concentration is 2.4 times 10 to the negative third moles of F minus for every 1 liter, that would get me how many moles of F minus I have dissolved. It's not asking that though. It's asking for moles of MgF2. So in this case, the balanced equation here is going to be really important because it's a 2-to-1 mole ratio. So I have 2 moles of F minus for every 1 mole of magnesium fluoride that dissolves. Okay, so I've got moles of MgF2 for what I'm solving for. Everything else cancels out with the units. And if I put this into my calculator, honestly, the math on here should be pretty easy for you to do in your head. Think about this as 0.1. So we're going to change the exponent here to 2.4 times 10 to the negative fourth, and then divide that by 2. So that'd be 1.2 times 10 to the negative fourth moles of magnesium fluoride. So what they're really doing here, I honestly think, is 2 things. They're going to see if you can get the correct number of moles, and on this FRQ, this would be worth 1 point. And then acknowledging this mole ratio is the second point on here. So there's a lot kind of going on in this problem that they're checking to see. Okay. Now, step 3 here says to determine the value of the solubility product constant KSP at 25 degrees. So here's why we're here in the first place. Alrighty, so we know that our KSP value is going to be equal to my concentration of magnesium plus 2 times the concentration of F minus squared, okay? Now, they gave us the concentration of F minus in the problem. They tell us that the concentration of F minus is 2.4 times 10 to the negative third molar. So I'm going to just put that right in here. Don't forget to square it here. Now you say to yourself, I do not have the information for the amount of the magnesium ions in here, but here's what you do know. This is my concentration of the fluoride ion. My magnesium concentration has to be half of that, because if you think about our ice table, the change here is going to be a plus 1x. This is going to be a plus 2x. So my concentration at equilibrium of my F minus is twice as big as my concentration of my magnesium. So I'm going to get 1.2 times 10 to the negative third here. And if we put this into our calculator, it's going to be 6.9 times 10 to the negative ninth. So that's our KSP value. Okay. I guess I want to give you a word of caution for something I see people doing sometimes, because it is really common. Like, I really see this happening a lot. Okay, so here is our ice table set up for this. We ignore MgF2 because this is solid. And then if we're starting off with nothing here, those would be zeros. We know that this is a plus x and a plus 2x based on our table. And so our equilibrium values are x and 2x respectively. So what I see people doing sometimes, if they're not reading carefully, is that they will take the concentration of the thing that's 2x and accidentally multiply it by 2. So what I mean by that is, in this problem, they are telling you 2x, the equilibrium concentration of F minus, is equal to 2.4 times 10 to the negative third molar. They are telling you that. That is equal to 2x. And that's, of course, why x for magnesium is equal to 1.2 times 10 to the negative third. Okay? But what I see people doing is when they put it into their equilibrium expression to get the K value, they'll do 1.2 times 10 to the negative third, and then accidentally they will throw in the 2x because they think that this is x, but it's not. This already is 2x. So they'll go 2 times 2.4 times 10 to the negative third and square that, and they'll get it wrong. So be careful that you are paying attention to what chemical you have and what that is in your ice table. So since they gave me my concentration of F minus at equilibrium, I know that is 2x. So when I put that into my equilibrium expression, it is my concentration of F minus. I don't have to double it or anything like that. This case, you don't actually even need the ice table. You just need to understand the stoichiometry of it. But this is a common mistake I see people making. So you just have to be very careful that you're reading your problems. And we will do a ton of practice with this stuff in class, so it shouldn't be too bad, but I just wanted to make you aware of it. Okay? So if you have any questions, let me know. Otherwise, good luck.